All right, guys, so this first question might be a good recap if you had any trouble with finding the equation on the quiz. There's an extra thing for this one as well. So we're going to find sine and cosine, but I want to start with cosine first, and then we'll talk about how we can get the sine function. So first things first, in these questions, we want to identify the max and the min values. So in this one, we've got 0 and -1. What would you guys do next? Carol? Okay, how would you do that? Great. So we're going to calculate max minus min over 2 to find the a value, which is also the amplitude. 0 minus -1, that becomes +1. And that should give us a half for a. What next? Tom, what would you do next? Okay. Awesome. So really it's just the center in between max and min, right? That's what we're finding. We're sort of almost finding like average of the max and min, which will give us the midline, the middle. So 0 plus -1 over 2 gives us -1/2. And I'm just going to sort of pencil this in here. We'll have to just sort of estimate where that is, which is okay. Okay. Next step. Lucas?
Next, you could look at how long it takes to take one full period. So this would be pi, as is, and then basically do 2 pi divided by pi, and put 2 as your k value, because you can look at the half.
Great. So find 2 corresponding spots, the beginning and an end of a cycle. Could be a max to a max. So if you did 0 to pi, that would mean that we can calculate our period. Technically, we're doing pi minus 0 to calculate that. You could also do min to min. If I wanted to calculate that, I would do 3 pi over 2 minus pi over 2. Another option could be like rising midline to rising midline. So if you know where this is and where this is, you can calculate that. So always bigger number minus smaller number. So here our period, we can calculate by doing, technically we're doing pi minus the lower number, which is 0. So that just gives us pi. And we'll use that, as Lucas said, to calculate the k value. So remember, guys, k is 2 pi over period. Sometimes we denote this with the variable b. And that means we have 2 pi over pi. And the pi's will cancel to give us 2. Okay, last part here, we're going to start with cosine. So how do I find d of cos? Oscar?
The d of cos,
Yep.
you're just like looking to where the top of the mountain is, which is what happens when you're at 0.
Yeah. So find a mountain peak, find a maximum. We could have also said pi. 2 pi could be another one. There's infinite answers. But yeah, because we have one on 0, that's nice. So we'll just say,
That's just d is one d.
yeah, we'll just say 0 for d of cos. This question also asks me to find this as a sine function as well. So for a sine function, as we sort of reviewed before our quiz, I'm going to trace along here until I find a rising midline, which happens like right here. It starts rising up into a mountain, right? I don't really know exactly where this is. It looks like it could be like one of the pi over 4 values maybe, but I'm not 100% sure. So there was a little method that we used last year in grade 11 to do this. If I have one d value and I need the other one, does anyone remember how we did this? Okay, I'll give you the starting point. So right now we have a cosine equation and I want to figure out the d value to make it a sine equation. the d of sine should be equal to d of cos. Does this ring a bell? Minus, in grade 11 we did minus 90 over k. And that's because the sine and cosine functions are 90-degree shifts of one another. And then we take into consideration any stretch or compression, horizontal stretch or compression that could have happened. Now, if we used 90 over k in grade 11, now we're in radians, so we're going to use pi over 2 over k, which we can simplify to. So if I have pi over 2 over k, think of this as k over 1. Oops. Think of that as k over 1. We have pi over 2, flip and multiply, times 1 over k. So we get pi over 2k. So I'm going to subtract pi over 2k. And the reason why I subtract, so we consider the original shifted versions of the original sine and cosine function. We consider any stretch or compression that has happened. And I'm subtracting because I know the d of sine will always be further to the left than any maximum, because I'm looking for a rising midline for sine, and that always happens to the left of a maximum, right? It rises up into the maximum from sine. So we subtract because it's further to the left. The rising midline will always be further to the left than the max. So we can probably also say, if we were to do the reverse, sine to a cosine, which we don't need for this one, but we may need for a future one, we can calculate d of cos by doing what? What would we do? Just as a guess. Oscar, what do you think?
Well, this is a little different than the cosine sine, actually. Is it like pi over 2k simplified plus the d of sine?
Yeah. So d of sine, and instead of minus pi over 2k, we do plus pi over 2k. Because if I have the rising midline, the max is always going to happen to the right of that, because I rise up into the mountain from the rising midline. So for this one, to make sure we get the correct d of sine, I'm going to use this first little formula here, because we already have d of cos and we have the k value. So let's see what we get for d of sine. So d of sine should equal d of cosine, which is 0, minus pi over 2 times k, and k was found as 2. So here we're getting negative pi over 4. Or in other words, pi over 4 to the left, right? Does that make sense? Does that look accurate for where this is, Lucas?
I'm just a little confused.
Sure.
So you're going cos to sine, but then you're doing sine is equal to cos. Is there like, it looks backwards to me, but why is that again? Sorry?
So sorry, I'm not sure exactly what you're asking here.
You're going sine to cosine, but right below it is cosine to sine.
So these are two different options, right? This one I will use if I have the cosine equation information and I want to make it into a sine equation. And then this one I will use if I have the sine equation information and I want to make it into cosine.
Okay. So can I just like point to it? I'm a little confused. So is this equals that?
So if I have cosine information and I want to make it into a sine equation, I have to find the different d value, right?
Okay.
So if I have the d of cosine already, I can find the d of sine by doing d of cosine, the one that I already have, minus pi over 2k. Does that make sense? Are you sure?
Yes.
Okay. Okay, so we're just going to plug them into the equations now then, guys. So a value was half. Maybe we'll do cos first because that's the one we found first. So cosine has a d value of 0. I'm just going to put kx here. There's no need to have x inside the brackets when we don't have a plus or minus in there. It's just plus 0. Okay, and then for sine, same thing, except we do have a d value shift for this one, so I'm going to put it as x plus pi over 4. Remember to switch that sign when you put it in. Oscar?
Why aren't you writing it as 1 over 2?
So we don't flip it when we put it in. We only flip if I were to take it from the equation and use it to calculate transformations, let's say. But we don't reciprocal it once we find it using this equation. This is actually the k value here. Yep. So there's our solution. Okay, so similar type question here, create a sine function, except this one, we don't have to pull out the information from the graph. The information is just listed for us here. So what can you guys pull out of this if we're told that the sine function has amplitude of 7, period of pi, phase shift of pi over 4 right, and vertical displacement of 3? What information does this tell me about A, K, D, and C? Sure.
A is going to be 7. K is going to be,
That's okay.
it's going to be 2.
Okay, so we'll do 2 pi over period, which is pi, and we'll get 2.
And then the phase shift is going to make it look like x minus pi over 4.
Sure. Yep. Great. When I create a function notation or y equals, just have something on the right side to make that an equation. So if you want to use f at x, you can use y as well. X, and as Oscar mentioned, we have to flip the sign of that d value when we put it in. So it should look like minus pi over 4 in the equation. The second part of this, which is on your reverse page there, asks us to create this as a cosine function. So everything should remain the same except the d value for cosine. And that's where these nice little formulas up here come in handy, is that if I don't have a graph and I'm just given this, instead of having to graph this whole thing and figure out where the maximum is, I can just use that little switching formula and I can switch it over to a cosine function. So right now I'm going to use this one because we have a sine equation and we want to make it into a cosine equation. So I'm going to calculate d of cos by taking the existing d of sine and adding pi over 2k. So existing d of sine is positive pi over 4. It's pi over 4 to the right. And k is 2, so I'm going to have 2 times 2 here, which is going to give me pi over 4 plus pi over 4. Add the pi's. Sure. Okay, so we'll get 2 pi over 4 and reduce to pi over 2. Good. So this tells me right shift, right? If it's positive. Okay, so same function as above, just switch the d value now. So I'm going to have the same AK DC values. Okay, and then of course, if I have a positive pi over 2, when I plug it in here, we make sure we switch that sign. And then change the sine to cosine, obviously. Good, any questions? Okay, transformations. Same as we do all transformations, same as what we kind of reviewed in our polynomials section. If I'm transforming a sine function, I'm just going to use the main quadrant separators as my x coordinates, the 0, pi over 2, pi, 3 pi over 2, and 2 pi. I don't need all the halves and negative halves. That's a lot of points. We don't need that many. So we're going to start with the parent function. I'll call it f at x equals sine x. And we're just going to use those special quadrant separator values here, as I mentioned. Okay, I don't have to memorize the parent function points as long as I know how to set up that radian circle. Caleb, can you just shut the back door there for us? Thank you. As long as I know that radian circle, I'm just going to take the ones right on the edges. And then how can I get my y's? I don't want to memorize them. So how can I get them if I know the x's? Carol? Put it right into your calculator, right? So make sure you're in radian mode. You're just going to enter sine of each of these, and that should give you the y coordinates. You might remember them from last year, which is great too, but if you don't, plug them in. So we should get, if we plug each of these into our calculator, 0, 1, 0, negative 1, 0. There's our parent function. Transformed function. I'm going to leave myself a little bit of space, a little bit more space on the x side than the y side here. We're going to have to do a little bit of fraction work in there. The equations, just to remind you for transformations, reciprocal of k times x plus d and ay plus c. So who can set these ones up with the numbers in our actual equation here? Using these. I know some of you know, you're just not offering the answer. How do I set these up? Or just give me one out of the two. Sophia. Awesome. Awesome. Yes, and switch the sign. Good. Great. Let's do the y's first. The y's are nice and easy. Take each of your y's, multiply them by 3, and add 1. Okay, all the zeros, of course, should be the same because we're plugging them into the same equation. So 3 times 0 plus 1, all of those will become 1. 1 times 3 plus 1 is 4. Negative 3 times, or negative 1 times 3 plus 1, negative 3 plus 1 gives us negative 2. All right, the x coordinates. We're going to do a little bit of fraction work here. So I'm going to take you through. Sorry guys, I'm losing my voice a little bit here. All right, take your x's. We're going to sub each one in here. So first one is 0. 0 times a half plus pi over 3. That one's nice and easy. We just get pi over 3. Leave a little bit of space over here for yourself as well. Or on the other side, doesn't matter. Okay, next one, plug in pi over 2. I'm going to get pi over 4 plus pi over 3. Common denominator is 12. This side gets multiplied by 3 to make it 12, so 3 pi. This side gets multiplied by 4 to make it 12, so 4 pi. So we get 7 pi over 12. Okay, pi is the next one, so we're going to plug in pi here, plus pi over 3, get pi over 2, plus pi over 3. So same fraction rules as always. Doesn't matter that there's pi's in there, right? It's okay. Common denominator is 6's. This side gets multiplied by 3 to make it 6. This side gets multiplied by 2, so we get 2 pi. 3 pi plus 2 pi, 5 pi over 6. Okay, almost there. 1/2 times 3 pi over 2 plus pi over 3. I get 3 pi over 2 times 2, which is 4, over plus pi over 3, not pi over 4. Okay, again, common denominator here will be 12. So multiply your left side by 3, we get 9 pi. Multiply your right side by 4, we get 4 pi. 9 pi plus 4 pi, 13 pi over 12. Last one, 1/2 times 2 pi plus pi over 3. The 2's will cancel, we'll just be left with pi plus pi over 3. Common denominator, we'll use 3 as the common denominator there. So this one doesn't need to change, the one on the right. Left one, I would have to multiply top and bottom by 3. So this will be 3 pi over 3. 3 pi over 3 plus pi, 4 pi over 3. Okay, tiny bit more tedious with the fraction work in there than our usual transformations, but I know you guys can do it. It's just your usual fraction work, right? So just common denominator, add them together, you got it, okay? Here's maybe a slightly more complex part of this. Where do I place 7 pi over 12 on here? That's the more complex part, right? So I've got a little trick to help with that. The trick is, the key here really is, how many units on the x-axis is pi? If we look at this graph, how many units do we have to count over to get to pi? Mathuccini? 6. So 1, 2, 3, 4, 5, 6. This is the key. If I can figure out what pi is on my scale, I can figure out where to place any of the other ones. So key relationship is that pi equals 6 units on the x-axis. Okay, we can also visually see here that pi over 2 is 3 units, so we can see that. What's 1 unit? If pi over 6 is 6 units, what's 1 unit? Pi over 6. So literally I would just divide by 6, right? I would get pi over 6. This one's really the same units that we've been using to graph like our primary ratios and everything as well, right? It's just going up by pi over 6's. So let's say I want to know what pi over 3 is on my axis. And I know pi is 6 units. I'm going to do a calculation. It will be 6 units, which is pi, divided by 3. And that should give me the number of units that I would need to count over on my x-axis to plot that point. So this one is 2 units over on my x-axis. We might have already known that because we used it in some previous graphs as well, but that's the idea. Okay, that's the little trick. Makes it really easy to plot your points. So 2 units, I'm going to plot that at 1. So this is pi over 3 is what we said. That's going to go at 1. We haven't graphed the parent yet either, so we'll have to graph that in a second. Okay, this one's 7 pi over 12. That one's a little bit more complex, right? That's okay. We'll just do 7 times 6 units, divide by 12, and how many units would we get there? Units, Jess? I don't think it's quite 4. Oscar, what'd you get? 3.5 units, yeah. 42 divided by 12. Okay, so at 3.5 units, I'm going to count that over on the x-axis. I'm going to plot it at 4. Okay? So 1, 2, 3.5. Plot that point right at 4. It's right here. Okay, next one, 5 pi over 6. If I want to calculate the units, 5 times 6 units over 6 should just really leave me with 6 and 6 will cancel. I have 5 units. So 5 units, I'm going to count 5 units over and plot that point at 1. 1, 2, 3, 4, 5 at 1. You should start to see a pattern develop within your x's. What do you guys notice about the distance in between every single number of units here. How many units apart are all the points? So far, at least. 1.5. So every time I'm adding 1.5 units to get to the next one. I can just continue that, right? It should all be equally spaced because all of these are pi over 2 apart, or in other words, 90 degrees apart, right? If we think about it in degrees. So let's just finish this up. I'm going to add 1.5. I'll get 7.5 units. And then I'm going to add 1.5 one more time, and I'll get 9 units. Done. So let's plot the last 2 points. Jess? Yes, it should. Thank you. 6.5, and then that makes that 8. Sorry about that. Okay, you can double check it as well if you want. Just plug in 6 units for each of those and multiply and divide, and you got it. Okay, so 6.5 units at -2. So this is 6.5 at -2. Pi is 6, right? So I just went 1 over from that. And then 6, 7, 8, back up at 1, right here. Right before the 3 pi over 2. So there's our first cycle. If I want to continue the cycle, I can keep adding 1.5 units, and then I'll just continue the pattern. So even if you wanted to, you could continue your table of values and just keep adding 1.5 units. So the next one should be at 9.5. And then this is the start of the next cycle. It goes to 4, right? So this will be at 4. If I want to keep continuing, I'll add another 1.5. This will be 11 units. And the next one will go to 1. The y values will repeat. That's the nature of a periodic function, is that the y values will always start to repeat. So you can do that, or you can just do it visually on your graph. You can say, okay, I see that this is a full cycle. The next part of this cycle goes over 1.5. It goes up to a maximum. So that's what we'll do to extend here. So that one should be right up here. Okay, next part goes down 1.5, or over 1.5 units, I should say, and down to 1. So that should be right here. Oops, wrong color. Okay, so continuing that down. Another 1.5 units over will go down to -2. So count yourself 1.5 units over, -2. Okay, so that's that part. And then back up to 1.5 units over, back up to 1. So that is right here, right before 5 pi over 2. Okay, and then that's 2 full cycles there. Okay, we're also asked in this one to graph 2 cycles of our parent function. So you guys practiced actually drawing this parent function on your quiz. So here's our first 5 points that we can use. So 0, 0, pi over 2 at 1. Pi is 0. 3 pi over 2 at -1. And 2 pi. That's 1 cycle. And then we'll need to extend maybe back into the negative section to get our second cycle here. Okay, nice smooth curves here, no zigzags. Okay, so I'm just going to extend this back this way. So moving from this backwards, this should go in the same motion, backwards. You can also enter them into your calculator if you're not sure. Just do sine of -pi over 2. You can do sine of -pi, should give you your points. I like to just do it visually by looking at the pattern. So this one will go back up to 0. Okay, next part will go up to 1. It'll go up to 1 there. And then back down to 0. All right, so that's our second cycle for sine. So I'll call this f at x equals sine x, and this will be our parent. call it y, or you can change it to g at x if you want, or whatever. All right, so this is the key. Pi, find where pi is on your scale. Could be a different scale. I can still do it though. Just find how many units pi is, and then you just calculate that number of units when you have all your pi expressions for your x coordinates. Does that make sense? Any questions? Okay, the second one is the same, guys, so I'm not going to do 2 today. I think we sort of get the hang. Unless you guys want me to do you want me to do a second one, or would you rather just, it's up to you. We can just finish off with this bottom part, and then you guys can actually practice one on your own if you want before you go. Okay, let's just do that. Okay, so last little part here, even and odd functions with trig. Who remembers, I'm taking this back all the way to unit 1, who remembers what an even function and an odd function are? Remember, that's different than even degree and odd degree. Even function, odd function. Jess? So that's degree, right? Then we classified, we had the degrees, and then we further classified into even function, odd function, if they had specific properties.
Wasn't the even function was over the y-axis, and then the odd function was origin? Was that the intersect of the origin?
So it's talking about symmetry, right? So symmetry, even symmetry, symmetrical over the y-axis, odd symmetry, point symmetry over 0, 0. So I'm going to draw 2 graphs. One is sine, one is cosine. And I want you to tell me if these will fit into even function, odd function, or maybe neither. So here's the sine graph. Here's the cosine graph. Do these fit into even function, odd function? Would they be neither? What do you think? Alicia? All right, so we've got symmetry, mirrored symmetry on either side of the y-axis here. That makes cosine an even function. Basically what it means, guys, is that the positive version of a theta and the negative version of a theta would equal the same y value. Okay, so we can actually see that here. So basically the definition says that cos of theta is equal to cos of the negative version of that same theta. Cos of, let's say, this would be pi, cos of pi, and cos of negative pi give me the same value. You can test it on your calculator if you wanted to. And then Alicia rightly said that this is the odd function because if we rotate 180 degrees, then we have symmetry. So this is point symmetry on 0, 0. That makes this an odd function. And basically what we're saying in this scenario is that the positive version of a theta and the negative version of a theta will actually give me the same y value, except one will be positive and one will be the opposite of that, negative. So for instance, if I use, let's say for sine, we use pi over 2 and negative pi over 2. I've got 1, and this one's equal to negative 1. They give me opposites out. So the definition of this would be that sine of any theta is equal to the opposite of the sine of the negative version of that theta. So that's what the kind of definition is there. Okay, so point symmetry on 0, 0, line symmetry over y-axis. All right. we will stop it there for today.